Well, welcome back to our Algebra 2 and Precalculus series. This is lesson 5 about polynomial and rational functions. Last time we just talked about functions and graphs and whatnot. This time we'll be talking in specific about a polynomial function. And then we'll move on to rational functions, which are sort of related to polynomials, but very different. So what are we waiting for? Let's get right in. First, quadratics. We talked about quadratics a bit before, quadratic equations, etc. Now we'll be talking about quadratic functions. First of all, a polynomial function is basically the sum of these terms. And it's hard to explain in a concise way, so I'll just give you what this means. This is a term. A(n) is the coefficient. You might recall this from Algebra 1. This is the variable x, and this is the power n. So this is actually the leading term, basically the first term in standard form. This is the degree of the function. The degree is the greatest number of power. So if it was x squared plus 3x plus 1, 2 would be the degree, the leading term would be x squared, the coefficient would be 1, the coefficient would be 3, the constant, which is this term right here, is 1. We can categorize it by the degree, like I said. The constant is when n is 0. Linear, we talked about, n is 1, so it'll be something in the form of ax plus b. Quadratic is when n is equal to 2, so it'll be ax squared plus bx plus c. We've talked about this before. Cubic is ax cubed plus bx squared plus cx plus d. And then finally, last but not least, the quadratic, ax to the power of 4, b plus bx to the power of 3, plus cx squared plus dx plus e. And then there's also quintic, sextic, probably, I don't know. But these are the main 5. Well, I guess a. That's the constant function, a. These 5 are the main ones we'll encounter. The zero polynomial is f of x equal to 0. And as you can see, it's a very difficult polynomial to memorize. That was sarcasm. The y-intercept of a polynomial is always 0, comma a of 0, which is basically the constant term. Because if you plug in 0, this becomes 0 because it has an x, this becomes 0 as an x, this becomes 0 as an x, everything in between becomes 0 because it has an x. The only thing that doesn't have an x is this, so it'll just be the constant term. Polynomials are always continuous unless otherwise stated. And we talked about briefly about continuity. Basically, you can draw it without lifting your paper off the pencil. A quadratic function, actually the main topic of the slide, is f of x equal to ax squared plus bx plus c. Look familiar? Hopefully it does. The parabola is the graph of the quadratic function. And you might have heard that term before. It basically looks something like this, a U, sort of. The axis of symmetry, let me draw my U again, because this time it looks better, is the line of reflection, which would be this mid line right here. Because this side, when you reflect it to this side, it is always the same. The vertex is the maximum or minimum of a parabola. So here's the vertex. In this case, it's a minimum because it's the least value. But you can also draw it like this, and this will become the maximum. Okay, time to destroy my beautiful drawings. The vertex form is f of x equal to a times x minus h squared plus k, where hk is the vertex, and the axis of symmetry is x equal to h. Briefly, it's basically saying that this is the vertex, h comma k. Oops, h comma k. So if I had a graph with the vertex of 1, 2, and I knew that a is 1, let's just ignore a for now. It'll become y is equal to x minus 1 squared plus 2. Easy. The a comes in a bit later. So an application of quadratic functions is projected objects. And this is a physics application. We've talked about geometry and we've talked about, I don't know, mixtures, motion. That's also physics technically. But yeah, projected objects. The height, which is labeled with S, I know that's misleading. It should be H. Physicists are weird. The height of a projected object with initial height of S sub 0 and initial velocity of v sub 0 is given by s is equal to negative 16t squared plus v sub 0 t plus s sub 0. So this is the y-intercept, as we can see. And that's because an initial height of that. So basically when time is 0, the y-intercept is s sub 0. The initial velocity is this. When you get into physics, you'll understand this. But for now, we can't talk about it. Maybe I can prove it in calculus because you're going to need derivatives. And then height, this negative 16t squared is a formula for gravity in feet per second. You're probably familiar with negative 9.8 meters per second. In feet per second, it's something like negative 32, I believe, negative 32 feet per second. And then you'll have to take a half of it. Again, physics related. I can't really go in depth, but here's the equation. You probably would need it if you're taking some sort of math, Algebra 2 class or Precalculus class. And remember, I'm only spending like half a slide on quadratic functions. Your teacher will probably spend at least 2 or 3 sections about quadratic functions. You'll probably go more in depth there. So if you're taking this for class and you just don't want the basics, then you're probably going to need to read your textbook or learn some more topics in quadratic functions. This is just the bare minimum. Okay, we're done with quadratic functions. We'll get back to polynomials. First, division. We've talked about addition and subtraction earlier. We've talked about multiplication earlier. We've talked about factoring earlier. Now division. Division is basically given f of x and g of x, with g of x is less than f of x. It's supposed to be of lesser degree. I just forgot the degree. It's fine. Of lesser degree. F of x is equal to g of x times q of x plus r of x. You're probably like, whoa, what all the functions? This is the original function. This is g of x. So these two we already knew. Q of x is the quotient, and r of x is the remainder. And it's key that the degree of r of x is less than that of g of x. Because you can't have, similar to how we have like the remainder is always less than the original number you started with, or sorry, if you're given like 30 divided by 5, the remainder is always less than 5. Similarly, the remainder is always less than, in quotation marks, than the g of x. Special case of division algorithm is when you're dividing by x minus k, basically a linear function. And in this case, the r of x is just r. It's a constant because the degree has to be less than that of the linear function. Synthetic division. So this is basically a form of division where you omit the variables and you're using only coefficients. So I'm going to talk about synthetic division first, and then I'll go back to long division, which is where the division algorithm has to come. But it's a bit more complicated, so I'll start with easy synthetic division. So it omits the variables, only coefficients, and you sort of do a division sign first. And let's say you had 2x squared plus 9x plus 3. Actually, let's do it cubed. Okay, I don't even know what the answer is going to be here, but let's just try. X minus 2. So what you do is you write the 2 over here, because you have the x minus 2. So basically, if you have x minus k, actually, let's do k, because we have this thingy right here. X minus k, you put k up here, just k. If you have x plus k, you put negative k. So anyway, we have 2 up here, and then you have 2x cubed plus 0x squared plus 9x plus 3. But this doesn't have anything to do with the variables. So you take out the variables, and voila, you're left with just the coefficients and the constant term, of course. So what you do next is you this is the complicated part. You bring the 2 down. Okay, that's simple enough. And then what you do is you multiply 2 and 2 to make 4. So you basically multiply this with that and 4. Now you add these 2 up and you get 4. And then you multiply 2 and 4, these 2, and you get 8, 17. Then you multiply 2 and 17 to get 34 and 37. And then that's where we stop. So that means our final answer would be 2x squared plus 4x plus 17, remainder 37. And I guess I'll just give you a second to copy that. Then again, this is a video, so you can pause if you want to, but feel free to pause whenever you want, to rewind whenever you want, and basically just do whatever you want. This is a video, not an actual lecture. All right. So now that we're done with synthetic division, I'll probably just give you another example, actually. So let's do 4x to the power of 4 plus 3x to the power of 3 plus 2x to the power of 2 plus x plus 5. I'm really creative today. And then we're dividing by x plus 1. So here's the thing about synthetic division. You can only divide it by linear. When you're trying to do x squared, dividing by x squared, then it won't work. So you put -1 up here. 4, 3, 2, 1, 5. Those are our coefficients. Bring the 4 down. -4, you add them up, -1, 1, 3, -3, -2, 2, 7. Hey, that looks pretty nice, doesn't it? Remember, if you have any questions, just leave them in the comments and rewatch the video until you get it. Wow, I feel bad for you if you have to rewatch the video and listen to my voice throughout the day. What a pity. Okay, so this is our final answer. The R is 7, and the quotient is 4x cubed minus x squared plus 3x minus 2. Voila. Like I said, only dividing by linear binomial in the form of x minus k. Okay, I told you I'll come back to long division, and that's what I'm going to do before we get into the remainder theorem. Oops. Okay. So again, give me a random polynomial. 3x cubed minus 6x squared plus 9. And dividing it by 2x plus 1. Yeah, again, for synthetic division, you can't divide it by this because this isn't in the form of x minus k. You need it to be in that form. You can't use synthetic division to do this. So if you want to do long division, it's basically sort of like long division in using numbers, except I love it. It's my favorite form of polynomial division. I prefer it to synthetic division. It just helps you understand more. So first, you want to multiply this by something. Okay, you know what? Since it's our first example of this, I'm going to make it a teensy bit easier on us. I'm going to make it 4x cubed. So 2x plus 1 times what goes into this? So 2x, well, first let's look at just 2x and this. 2x times what goes into 4x cubed? Well, 4x cubed divided by 2x is 2x squared. So that'll be our first term, 2x squared. So as you already know, that's 4x cubed. 2x squared times 1 is plus 2x squared. And then you subtract it. So once you subtract, you can cancel this term off and you'll get negative 8x squared plus 9. Again, you work through it. 2x goes into 8x squared, negative 4x times negative 4x. So I'm gonna move it a bit over here, erase our original polynomials. Sorry, polynomials. And then have this again, negative 8x squared plus 9. Well, when you multiply by negative 4x, you get negative 8x squared minus 4x. And subtract, you get 4x plus 9. So 2x times what goes into 4x? Well, just plus 2. I'm going to move it up here. So we have 4x plus 9. And subtracting 4x plus 2, you get 7. So the remainder is 7. Ooh, the previous one was also remainder 7. That's nice. So here's our final answer. I'm going to erase this part right here. We have 2x squared minus 4x plus 2, remainder is 7. And that's our final answer using long division. We can't use synthetic division on this because it's the 2x plus 1, but no matter, long division is lovely. Remainder theorem, finally. If f of x is divided by x minus k, then the remainder is f of k. You might be wondering how we did this, but I'm not going to prove it to you right now because it's going to take a long time. And I don't have that much time, neither do you, because this is supposed to be a review video. Or a preview if you're not in Algebra 2/Precalculus yet and you just want to get ahead, then I congratulate you. Anyway, if I have, for example, 2x squared plus 1, and you divide it by x minus 1, then the remainder should be 2 times 1 squared plus 1, because it's x minus 1, and you plug in the 1 over here, you get 3. Now, is that the remainder? Well, we shall see. Here was our prediction, 3. So now if we use synthetic division, oh, hold on, let's see what we actually did divide by x minus 1. Then we can use synthetic division. Now I better use the eraser. Two x squared plus 0x plus 1, and that's 1. So I'll get rid of the x's, don't you worry. You bring down the 2, 2, 2, 2, 3. And that's a remainder. Wow, we're right. It's 3. So it's basically 2x plus 2, remainder 3. And whenever you synthetic divide, the last term will always be the remainder, and everything before it would be the coefficients for the previous one. So yes, the remainder theorem works. A sort of corollary, if you've taken our geometry course, you probably know what that means. A sort of derivation of this, and another thing that you can derive out of this is that f of a minus f of b is divisible by a minus b. So if I have, again, 2x squared plus 1, that means f of 2 minus f of 1 is divisible by 1. Okay, that's a horrible example. F of 10 minus f of 6 is divisible by 4. And let's try it out. 10, if you plug in 10, you'll get 201. If you plug in 6, you'll get 73. You subtract them, you'll get 128, which is divisible by 4. So yes, that's a vague example, but it works. It works. Potential zeros of a polynomial. So to determine whether k is a zero of f of x, you use synthetic division to divide f of x by x minus k to see if the remainder is 0. And if the remainder is 0, that means that f of k is 0. And f of k is 0, meaning that it's an x-intercept, which means it's a potential 0. Wow, I love it. So the factor theorem, so basically some more polynomial theorems on this slide. The factor theorem says that if f of k is 0, then x minus k is a factor of f of x. So it's sort of like, hey, now we know f of k is equal to 0 from the previous theorem. But now what do we do with it? Well, this one's saying that if you know this, then x minus k is a factor of f of x. The rational zeros theorem. This one is basically the lifesaver in polynomials. If p divided by k is a rational zero of f of x, then p is a factor of a is 0, and q is a factor of an. So if I have a pretty complicated one, let's do it. 3x squared cubed minus 6x plus 9. Why not? We probably did this one already, but not sure. You want to find the rational zeros, basically. Everything rational, as we covered in the first lesson, is basically it's a fraction. So you know that p is a factor of 9. So it'll be plus or minus 1, plus or minus 3, and plus or minus 9. Q is plus or minus 1 or plus or minus 3. So that means p divided by q, if we have 1 and 1, it'll be plus or minus 1. 3 and 1, it'll be plus or minus 3. 9 and 1 will be plus or minus 9. 3 and 3 will be plus or minus 3. 9 and 3 would be plus or minus 3. Sorry. 3 and 3 would be plus or minus 1. 9 and 3 would be plus or minus 3. 1 over 3 would be plus or minus 1/3. So these are the potential roots that we have. And this is actually a relatively short list. I know there's 8 in there, but in some cases you'll get 10s and 20 potential zeros, and that's when you give up. So if you really want to find which of these are the roots, you can plug in them one at a time. So plug in 1, 3 minus 6 plus 9 is equal to 0. And the answer is no, it's not. Okay, let's plug in -1. -3 plus 6 plus 9 is equal to 0. And no, it's not. Let me erase these. We can rule out plus or minus 1. What about 3? 81 minus 18 plus 9 is equal to 0. Nope. -3 is -81 plus 18 minus 9 plus 9 is equal to 0. And no, it's not. 9 will be way too much because 9 cubed is 729. Oh Lord. So I'll try 1/3. That would be 1/9 minus 2 plus 9 is equal to 0. And no, it's not. At this point, I'm going to give up because it's not -1/3 either. So it probably doesn't even have any rational roots. If you want, you can plug this into your calculator. I don't know, just solve it yourself maybe. And I'm pretty sure this doesn't have any rational zeros. If it does, I probably just missed 1 or 2. Sorry for the horrible example. I'll try better next time. But you see what rational zeros theorem does, doesn't it? It simplifies finding zeros a lot. The fundamental theorem of algebra. Woohoo! Every polynomial of degree 1 or more has at least one complex zero. Complex meaning I plus 2, I plus 4, I don't know. Complex involving I. So basically it's saying that it crosses the x-intercept at least once, even in a complex number. And that's going to bring us into complex planes and whatnot and fun stuff that are actually going to be covered, I would say, in our advanced mathematics course. It's not out yet unless you're from the future and it is already out and you're enjoying it as we speak. Well, it's going to be about number theory, combinatorics, and some other fun stuff. Number of zeros theorem. So a polynomial of degree n has at most, so note this word at most, well, two words actually, at most n distinct roots. It can have less, but it can't have more. The multiplicity of a zero is the number of times the zero occurs. So basically, let's say y is equal to x plus 1 times x minus 1, for example. Each of these roots occurs once. But if we add x plus 1 squared, then this root occurs twice. It's -1 and -1 again. The irrational conjugate roots theorem. If a root of a polynomial is a radical expression, then another root is the conjugate of the radical expression. So if I knew that, I know, root 5 minus 1 is a root, then negative root 5 minus 1 is also a root. Remember from our conjugates lesson, I believe that was one of the first two Algebra / Precalculus lessons. Complex conjugate roots theorem. If the root of a polynomial is a complex number, then another root is a conjugate of the complex number. So it's basically sort of like the same as the previous theorem, except let's say I replace root 5 with 5i. 5i minus 1 and negative 5i minus 1. So that's the main polynomial theorems, I believe. Oh wait, there's more. These ones aren't really theorems, but they're more like handy rules. Discard a rule of signs is basically helping us find the number of zeros. So the number of positive real zeros is either equal to the number of variations in signs or less than that by a positive even integer. So for example, if I have x4, x to the power 4 minus 4x cubed plus 7x squared minus 9x plus 3, the number of variations is 1 from positive to negative, 2 from negative to positive, 3 from positive to negative, and 4 from negative to positive. So it's 4, meaning that the number of positive real zeros is either 4 or less than that by a positive even integer, 2 or 0, either 4, 2, or 0. You would never know. And that's for the positive. For the negative, it's basically you take f of negative x, take the number of variations in that, and then you do the same exact thing. So I'll pull up a different function this time, 5x to the power 5 minus 4x to the power of 4 plus 7x to the power of 3 plus 9x squared minus x minus 5. So 1, 2, or wait, sorry. Let's take f of negative x first. So negative of this is negative 5x to the power 5 minus 4x to the power 4 minus 7x cubed plus 9x squared. Oh wait, I've got the 5 here. Plus x minus 5. So the number of sign variations, none here, 1 from negative to positive, 2 from positive to negative. So either 2 or 0. These are the number of negative roots. And note that these are only real roots. Vieta's theorem. Like I said, this isn't really an actual theorem. It's more like a handy rule. So you might not understand what's going on here, but if you remember from quadratics, the sum of the two roots is basically equal to negative b over a. So in this case, the sum of all the roots is equal to negative a of n minus 1 over a of n. If I have a of n, x to the n, plus a of n minus 1, x to the n minus 1, plus dot, 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 the sum of all the roots will be negative of this divided by that. And then the product, as you probably recall, is c over a. So in this case, it's the last term, which is a of a sub 0 over a sub n. It's actually either negative or positive, depending on the degree of the polynomial. If it was cubic, then it would be negative. If it was quartic, it'll be positive. If it was quadratic, it'll be positive. If it's linear, it'll be negative, so on. That's why there's a negative n to the power of negative 1 to the power of n. So if it's an odd degree, then it'll be negative. If it's an even degree, it'll be positive. And this last one is not familiar probably, but it's basically a of n minus 2 over a of n. This is the pairwise sums, basically x1 times x2 plus x1 times x3 plus x1 times x4 plus da 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 plus x2 times x3 plus yada yada yada. So let me clear all my drawings and then write them neater. And there we go. Copy it down, pause the video. I don't know. These are important. Polynomial functions. So a power function is basically f of x is equal to x to the nth. If n is odd, then it is an odd function. And the domain would be all of real numbers. The range would be all of real numbers, and it's always increasing. So I'm gonna do linear first. Oops, that was not. My lord. How hard is it to draw a straight line? Okay. Cubic looks something like this. And then quintic looks something like this. And then septic, seventh, looks something like this. And so on. It sort of maintains the same shape, except for linear. If n is even, the function is even. Domain is all real numbers. Range is not always all real numbers. I put it here because it's usually never all real numbers, but in some cases it is. Let me explain. I couldn't write the actual range here, which is why I wrote all real numbers, but just ignore that for a second. It's basically the range is y is greater than or equal to the lowest minimum. In this case, in a quadratic, it's just the vertex. In a quartic, it'll be something like this, which again is the vertex. And then you see a pattern. In this case, there's no exceptions like linear. This is probably something like 6th degree and so on. It's decreasing from negative infinity to 0 and increasing from 0 to infinity. Some transformations basically turn the power function into a polynomial function. So it's sort of like the same thing as the quadratic, except it's to the power of n instead of to the power of 2. Now we'll be talking about a. A is basically the vertical stretch or string. If it's greater than 1, the absolute value of it, it's a vertical stretch. If it's between 0 and 1, it's a vertical compression. If it's negative, it's a reflection over the x-axis. And the vertex is obviously a translation, HK. The behavior of the roots, when it's a multiplicity of 1, it crosses the x-axis. If it's an even, it bounces off in quotation marks. It basically looks something like this. I probably should change the color. So right here, it bounces off. It doesn't go through. In a linear, it would just go through. But in a quadratic, it bounces off. Odd multiplicity more than 1, it crosses and is tangent to the x-axis. So yeah, back to the same color. Cubic looks something like this. It crosses it and it's also tangent, meaning like it's sort of, if you zoom in, it looks like this. It's basically at that value for quite a bit of time. Meanwhile, linear would just be like that. A change in concavity occurs at odd multiplicities, more than one. Basically, concavity is the direction the graph opens. So this is concave down, this is concave up. So in a cubic, it starts off concave down, and then it goes up concave up at this point. The turning points are where the graph changes form, increasing to decreasing and vice versa. So there are at most n-1 turning points for an nth degree. Like we said, at most n roots, there's at most. So it could be less. The end behavior of a graph is basically the behavior as it goes towards at infinity and negative infinity. If it's odd, and if the leading coefficient is greater than 0, if fill in the blank, I'll show you in a while. But there's two separate cases. If it's greater than 0 and if it's less than 0. If it's greater than 0, that means that it goes towards infinity. If it's less than 0, that means it goes towards negative infinity. So this is just towards as x approaches infinity. But as x approaches negative infinity, x as x approaches infinity, y approaches infinity in this one, and in this one, y approaches negative infinity. For negative infinity, y approaches negative infinity, and y approaches infinity. Sorry for the confusion, but I actually made a vertical table and a horizontal table, which sort of ruined the point of making tables. In fact, if n is even, we still have two cases. So at infinity, this one would be y approaches infinity. At negative infinity, this one would be y approaches infinity. Not negative infinity, but infinity. For this one, it'll be y approaches negative infinity, and for this one, it'll be y approaches negative infinity. Whoop. So if you look on a cubic, you see that this is when the leading coefficient is greater than 0. It goes towards infinity and then negative infinity. If it was less than 0, then look like this. Towards negative infinity, and then, towards negative infinity and then towards infinity. You can do the same thing for a quadratic and see how the end behavior correlates. To graph a polynomial function, it's basically sort of complicated, lots of steps. First, you find and plot the zeros. Then you find and plot the y-intercept. Then you find the end behavior, multiplicity, and additional points. And then you graph it. So I'll do a quick example with you. X cubed minus 6x plus 3. So finding the zeros of this, use the rational roots theorem. It'll be plus or minus 3, plus or minus 1. If you plug in 1, you get 1 minus 6 plus 3. Actually, I do not think that this has any rational zeros. So I won't actually do an example here. We're running out of time. But I would encourage you to sort of find an example online and do it yourself before you see the example. You know how to find the zeros. You know how to find the y-intercept, and you know how to find the end behavior, multiplicity, and additional points. You just connect the points with the graph. So you might be wondering, what's the x-intercept, zero, solution, and factor got to do with each other? And there's also roots in the middle. So if c comma 0 is the x-intercept of f of x. So x-intercept is always in coordinate notation. C comma 0. Then c is 0, and it's also a solution to the function. And x minus c is a factor of the function. Intermediate value theorem. So if f of a and f of b have opposite signs, then there exists at least one real root c such that a is less than c, which is less than b. So it's basically saying given something like this, A is here, B is here, then there has to be a root somewhere in the middle. It's obvious. I mean, if you have a negative and then a positive, it has to cross 0 at some point. Boundedness theorem. If f of x has a positive leading coefficient and is synthetically divided by x minus c, if c is greater than 0 and all the numbers in the bottom row of division are non-negative, then there exists no real root greater than c. So you do the synthetic division and you get the numbers, and all of these numbers are non-negative. Then there is no root greater than c. Basically, c, it's sort of like saying that once you hit c, no more roots after that. So now you know all the roots are less than c. C is less than 0, and all the numbers in the bottom row alternate in sign. So again, you have all this. If they alternate in sign, then it's basically the lowest value. There's no root less than c. But remember the signs of c. C has to be greater than 0 for the first case, and c has to be less than 0 for the second case. This isn't used as much, but it's good to know. I personally have never used it in my math career. Rational functions. We spend the bulk of this lesson talking about polynomials, not rations. So a rational function is a quotient of polynomials. The reciprocal function is the most basic one, and it's basically just 1 over x. Domain is basically x is not equal to 0, it's odd and decreasing. The vertical asymptote of any rational function actually is f of x approaches one of the infinities as x approaches a. A is the value that makes the denominator equal to 0. So basically, it's a vertical line that the graph never touches. Horizontal asymptote, the function approaches a value as x approaches one of the infinities. Here are the rules for horizontal asymptotes. So if the degree of the bottom is greater than the degree of the top, it's the x-axis as the horizontal asymptote. If it's equal to the degree of the top, then it's the ratio of the coefficients of the leading terms. I'll give you an example in a minute. And the last condition is if the bottom is 1 less than the degree of the top, then it's a slant asymptote, and the equation of it is the quotient between p of x and q of x. First thing to do, here's a graph of 1 over x. Here is the vertical asymptote. There's only 1 in this case. And here's the horizontal asymptote. There's only 1 in this case. Next, for this one, if I had 1 over x, for example, then it's b is equal to 0. If I had x plus 2 over 2x plus 1, then b is equal to 1/2. Ratio of the leading coefficients of the leading terms. And if it's 1 less, so for example, if I have x squared plus 2 over x plus 2, then you basically divide them, find the quotient, and that's the equation of the slant asymptote. The inverse square function is basically f of x is equal to 1 over x squared, and it looks something like this. It has a vertical asymptote of y is equal to x equal to 0, and it has a horizontal asymptote of y is equal to 0. So how to graph rational functions? You basically find the asymptotes and intercepts. You determine if the graph will intersect the non-vertical asymptote. So a graph can actually intersect a horizontal asymptote, but for that, you need oscillations, and it's sort of confusing. So I won't really give an example here. It's more of precalculus, calculus type concepts. You plot other points if needed, and you graph. So for example, if I have something like x plus 1 over 2x squared, you find that asymptotes. Horizontal is y is equal to 0, vertical is x equal to 0. Intercepts is x equal to -1. So in this case, it does cross the non-vertical asymptote. Now you're gonna have to plot other points and then graph it. I won't do that here. I'll leave that as work for you. If you need to check it, then just use Desmos to graph it. The behavior near the vertical asymptote. So if x minus a to the power of n is the greatest power that is a factor of the denominator, we're talking about the denominator. If n is even and if n is odd, again, there are two cases. If n is even, then it goes to infinity on both sides. If n is odd, it goes to infinity on one side and negative infinity on the other. So like we said with 1 over x, for example, it goes to infinity on one side and negative infinity on the other. For 1 over x squared, it goes to infinity and then it goes to infinity again. If it's negative 1 over x squared, obviously it'll be reflected over the x-axis. Now we'll be talking about variation. It's basically a relationship between quantities. Direct variation is something you probably know from Algebra 1. It's basically proportionality. Y is equal to k times x. Inverse variation is something new. It's basically y is equal to k over x to the power of n. So for example, if I had like y is equal to 1 over x, that'll be inverse variation. Joint variation is y is equal to k x to the power of n, z to the power of m, dot, dot, dot. Actually, you can have any number of variables you want. These are pretty advanced. I probably won't go over them. But I'll give you an example of a variation problem. So to solve it, you write the equation, solve for k, and then substitute the remaining values to solve for the unknown variable. So let's say it's y is equal to k x squared. Why do I keep on saying that? K x squared z cubed. This is joint variation. So for example, if you know that when x equal to 1 and z is equal to 1, k is equal to 2. Sorry, y is equal to 2. Then yes, if you solve it, you get k is equal to 2. Then you can find the equation of it, and then the problem will be asking if x equal to 2 and y is equal to 4, then what would z be? And the answer is, well, you know, y is equal to 2x squared z cubed. You plug in 2 here and 4 here, so you get 4 is equal to 8z cubed. So z cubed is equal to 1/2, and you'll get a cube root. Z is equal to cube root of 1 over 2. And that'll be your answer. Next time, we'll be talking about some more important functions, exponential and logarithmic. We'll also talk about inverse functions, which is sort of another topic in functions that we need to talk about. If you have any questions on this video, feel free to go back, pause the video, take notes, whatever you want. I hope this helps you. See you later.